Recent advances in 3D object reconstruction have been remarkable, and 3D object reconstruction methods capable of real-time rendering are crucial for the creation of real-world content. Most reconstruction research has focused on improving algorithmic performance. For example, rendering time and visual quality. However, we need to know which reconstruction method can improve the user experience when used in real-world content, and whether the experience differs across platforms. We created the model using 3 different reconstruction methods. We used a smartphone camera to take videos of rotating objects from 3 angles: top, middle, and bottom of the object. In the 3DGS condition, we used the source code of the original Gaussian splatting paper. Using the background removed images, we performed SFM using CalMap to find image features, and we modeled 3D scenes from sparse point clouds after feature matching and bundle adjustment. We utilized the 1 2 3 4 5++ demo by to implement the single image to 3D condition. The marching cube algorithm converts it into a 3D mesh and texture, and you can input the texture color for a specific camera angle. The video 3D condition removes only the background of the input video, which can be the ground truth of our study in terms of visual quality. To make the objects appear as neatly segmented as possible, we implemented a chroma key technique that composited a green color into the removed background to make the object stand alone. In this study, we investigate the effects of 3 different visualization methods, including 2 real-time reconstruction methods, 3DGS, image to 3D, and video playback, on user recognition memory and experience on 2 different platforms, VR and PC. We designed a 3x2 experimental design to evaluate 3 reconstruction methods in 2 platforms. This is the result of 3 different reconstruction methods. This video shows a user wearing an HMD in a GSVR environment and interacting with an object created with 3DGS. Image 3D conditions could also be interacted with in the same way. This video shows a user interacting with an object created with video play in a video PC environment. Users thought it was so natural that they didn't even notice that it was a 2D video. The dependent variables are as follows. We conducted a survey asking 3 questions to identify objects: visual quality, task load, and usability. We found that objects reconstructed with 3DGS in VR environment and objects reconstructed with video in PC environment were more effective for memory. These results can be interpreted as the effect is maximized when the number of dimensions of the platform and the object match. In the 3DGS and image 3D conditions, some participants reported that it was very easy to manipulate the objects in VR by rotating them around, and that the 3DGS results were so close to the real objects that they felt like they were touching them in front of their eyes. On the other hand, the video 3D results were more difficult to manipulate, but the higher resolution of the results made it easier to identify objects. The main findings presented in this study can provide guidelines for designers who use reconstruction methods to create content in the future, which can be summarized as follows. First, different reconstruction methods have different positive effects on object recognition memory across platforms, with 3DGS being better for VR and video 3D being better for PC. Second, content that requires high visual quality is better suited for 3DGS or video 3D methods. Third, 3DGS or image 3D can improve usability and reduce task load for content that emphasizes user interaction. Fourth, image 3D method can be more useful when prototyping or using generative AI.